Take a look around you for a second. The phone in your hand, the chair you're sitting on, the very building you're in. How did they go from just an idea to a real physical thing? Well, it all starts with a plan, a blueprint. But this plan is written in a really special, universal language, one that lets anyone, anywhere in the world, build the exact same thing. And that is the language of engineering drawings. So, here's what we're going to do. We're going to build a simple part, virtually, from the ground up, just to understand this language. First, we'll cover why this language is so important. Then, we'll give our part its basic size. After that, we'll add some curves and holes. Then, we'll ask a really important question. How perfect does it need to be? And finally, we'll decide on its final feel, its texture. Let's get into it.
Okay, first things first. Why do we even need this stuff? This whole section is about tackling one of the biggest challenges in making anything. How do you get that fuzzy idea out of your head and turn it into a precise, concrete design that someone else can build perfectly?
I mean, really think about that for a second. It's a massive challenge, right? How can you communicate an idea with such perfect clarity that there's absolutely zero room for error, no chance of misinterpretation, no matter who is building it?
Well, you definitely can't do it with just words. That's a recipe for disaster. If I say, make it about this big, that's totally useless. My idea of a smooth corner could be way different than an engineer's in Germany or a machinist in Japan. Words are they're too fuzzy, too ambiguous for this kind of work.
The solution, though, is actually pretty brilliant. It's a shared visual language with super strict rules and symbols that everybody has agreed on. There's no guessing, no I think this is what they meant. It's basically like a musical score, but for manufacturing. And that is the whole point of an engineering drawing.
All right, let's start building our part. The very first thing you have to do is define its basic size. Before we worry about any of the fancy details, we've got to give our shape its fundamental proportions. This is square one.
And the most basic building block of this language is what's called a linear dimension. It's super simple. It's just the measurement of a straight line between 2 points. You can think of these as the nouns of the drawing: the length, the width, the height, the absolute fundamentals. And here's what that looks like. The height is 30 millimeters. The width is 70. See, there's no guesswork here. It's clean, it's simple, and it's totally unmistakable. Okay, so we've got a basic rectangle. Cool. But, most things in the real world aren't just simple boxes. So the next step is to figure out how to describe features like curves and holes. We've got to move beyond just straight lines.
Now, to handle anything circular, we use two key symbols. For curves on the outside of a part, like a nice rounded corner, we specify its radius, and we mark it with an R. But for features on the inside, like a hole drilled all the way through, we use its diameter, which has this special circle with a slash symbol. It's a simple rule of thumb: radius for outside, diameter for inside. And that little convention prevents a ton of expensive mistakes.
All right, now we get to a really crucial real-world concept. This is where the theory hits the shop floor. We need to ask ourselves, how perfect is perfect? Because in the real world, nothing is absolutely flawless, which brings us to the idea of tolerances.
I mean, let's be real. If a drawing says a part needs to be 50 millimeters long, can any machine on planet Earth actually make it 50.00000 with infinite zeros? No way. It's physically impossible.
So we have to define what's good enough. And that is exactly what a tolerance is. It's the acceptable amount of variation allowed for any given size. It sets the upper and lower limits for a part to be considered good. And this is a huge deal, because making something insanely precise costs a lot of money. So engineers use tolerances to make sure a part works perfectly for its job without costing a fortune.
So instead of just writing 50, the drawing will say something like this: 50.0 plus or minus 0.1 millimeters. This tells the machinist that any part they make that measures between 49.9 and 50.1 millimeters is perfect. It's good to go. It's both precise and practical.
We are so close to being done with our part. There's just one last crucial detail we need to add. We have to specify the final feel. This is all about controlling the texture of the part's surfaces. A surface finish symbol does exactly what it sounds like. It tells the manufacturer what the texture of a surface should be. Should it be rough, silky smooth, or maybe polished like a mirror? And this is super important for any parts that have to slide against each other or create a seal or just, feel good in your hand.
So how does it work? Well, the language uses these simple checkmark symbols. Think of it like a rating system.
One check might call for a standard kind of rough machine surface. 2 checks tells them to use a finer process to make it smooth to the touch. And 3 checks, well, now we're talking about grinding or polishing it until it's reflective. Each symbol is a direct command.
And there it is, our completed design. I know it might just look like a block with a hole in it, but because we used this language, its size, its shape, its required level of precision, and its final texture are all locked in, clearly and unambiguously, for anyone in the world to build.
So to quickly recap the big ideas, engineering drawings are a universal language designed to kill ambiguity. Dimensions, like linear, radius, and diameter, define the basic size and shape. Tolerances define the acceptable real-world range of imperfection, and surface finish defines the final texture.
So, we've just learned the basic grammar of this incredibly powerful language. But this leaves us with one final and pretty important question. Now that we know the rules, what happens when this so-called universal language is misinterpreted? What are the real-world consequences when a single symbol on a page is read incorrectly?